Thank you very much. I just want to quickly just put out there as a disclaimer that even though I do currently work at Facebook, none of the work that I'm presenting today is actually Facebook work, and I'm not representing the perspectives of the company in any way over the next 60 minutes. All the work that I'm presenting today was kind of done over the last 10 years through both my affiliations at University of Washington and then Sandia National Labs. And I also want to just call out the contributions of my collaborators, Kuchin Lee and Eric Parrish, who did a lot of the actual work in this talk. And so the overall goal of this talk, I know we're in the machine learning and dynamical systems special interest group today. It's really sort of trying to get at how we can use AI innovations in order to move our high fidelity extreme scale computational physics simulations towards executing in near real time. And so it's a kind of novel task in use of AI that has a very concrete application, which is trying to have these high fidelity models run much faster. And so over the next 60 minutes, I'm going to focus in on a few things that we've been working on towards this objective. So first, let's set the stage and provide some motivation. So as I'm sure many people here on the call are well aware, high fidelity physics-based modeling and simulation has become an indispensable tool across a wide range of applications in science, engineering, and entertainment because it provides a mechanism for accurately simulating the realistic performance of complex engineered systems, the performance of autonomous agents in an environment, as well as the physical movement of virtual characters in films. And as such, physical simulation plays not only a critical role in national security work done at my previous employer, but it plays a surprisingly large role in the world of tech. And so the issue here is that as we rely more and more on these simulations, greater demands are being placed on the fidelity of these simulations, right? We're not merely using these as a means to a greater end, where that greater end might involve some kind of like large scale engineering experimentation. In many cases, we're basing decisions purely on the output of these simulations. And as such, we need to really imbue them with high levels of predictive fidelity. And the way we do that is typically by imbuing them with fine spatiotemporal resolution, which can lead to computational models that have that are extreme scale in nature. It's not uncommon for a single simulation to consume months on a supercomputer, for example. And as a result, there's a de facto computational barrier that prevents us from using a lot of these high fidelity predictive computational models for a range of very important time critical applications. Like, for example, model predictive control. We require these simulations to execute in many cases at sort of the millisecond level in order to do receding horizon control, for example. Health monitoring, if we have some kind of infrastructure or engineering component that's out in the field, we want to do sort of real-time data assimilation in a digital twin setting. We may require also inverse problems to be solved on the order of seconds or minutes. For virtual interactions in VR, for example, we might want to enable the interaction with very complex rheology materials, which would require executing simulations again, essentially in real time. And finally, design optimization. If we want to sort of explore the design space in its high dimensional nature, we may require on the order of 10 or 100,000 simulations to execute in a week or so. And so even for that kind of application, which isn't real time, we still need to accelerate the simulations substantially. And the overarching goal of our work in this space is to really break this barrier so we can use these high fidelity models for these time critical applications. So to ground this a bit more, here's an application that I worked on at my previous employer. We call it the captive carry problem because it essentially simulates the long pressure exerted in a store when it's immersed in a three-dimensional cavity over very long time intervals. And so to get at this application, our analysts, Matthew Baroni and Srini Arunajedasan, developed a validated and predictive fluid structure interaction model. The fluid model on the right is a validated hybrid RANS LES model that's accurate to within 5% of experiments in our quantity of interest over a wide range of Mach numbers and angles of attack. But to achieve this validation result, which is quite nice, we needed a highly resolved mesh with around 100 million cells and 200,000 time steps. And this is very common in CFD, as RANS models are typically not able to accurately predict regions of separated turbulent flows, which can often occur in off-design conditions of existing aircraft and will likely occur in design conditions of future aircraft. And so as a result, a single simulation here consumes 6 weeks on 5,000 cores. And even when you have access to some of the largest supercomputers in the world, this can create an issue and you need to execute on the order of thousands of these simulations. And so the barrier that we face in this work is that of, again, the sort of computational barrier that prevents us from using this model for time critical problems. So whether it's exploring the flight envelope, performing uncertainty quantification, doing model predictive control, or robust design of the store and cavity, ideally, we'd like to accelerate these simulations by several orders of magnitude to really be able to tackle those goals. This computational barrier was also articulated a few years ago in the NASA High Performance Fast Computing Challenge, where they mentioned that despite tremendous progress made in the past several decades, CFD tools are too slow for simulating complex geometry flows, taking from thousands to millions of computational core hours. And the time critical problem that they articulated was multidisciplinary analysis and design, where they also explained that they wanted to increase the speed of computation by several orders of magnitude. And what they called out in this RFP is that they would like to accelerate calculations between 1 and 3 orders of magnitude. And I'll show you later in this talk how we actually have been able to achieve that goal for certain classes of turbulent flows. Okay, so how do we go about mathematically characterizing this computational barrier, breaking it down, and then solving it using methods from AI? So what we do first is we consider a very expressive, simple computational model that covers a wide class of physical systems. That is a system of parameterized ODEs. So let's imagine we have any kind of PDE that we've semi-discretized in space already, and there are certain parameters mu that define different instances of this initial value problem. This can represent problems ranging from magnetohydrodynamics all the way to separated turbulent flows. And so the idea here is if we have a system of parameterized ODEs and the underlying system model is high fidelity in nature, the dimensionality of the state vector is often on the order of 10 million or 100 million. And so what is a time critical problem leveraging this computational model? Really what it says is that we would like to rapidly solve where rapidity is defined by the time constraint of the application. We would like to rapidly solve this ODE for many different points in parameter space that I'm going to denote by D query. And you can think of each of these targeted points as defining a different set of boundary conditions, initial conditions, or designs of our engineering system of interest. And so this is our overall task. How do we go about achieving this or solving this task? The main idea that I'm going to sort of leverage throughout the rest of this talk is to exploit simulation data that we collect at a small number of these query points. And so unlike many applications in AI where we go out into the wild and we collect data, in this case, because our goal is to really solve that numerical model at many different points in parameter space, what we're going to do is collect simulation data at a handful of points, leverage that data to understand the underlying structure of the problem, and then leverage that structure in order to accelerate the simulation of our system at the remaining blue points. I'm not going to go into details today in terms of how we select these red points, but suffice it to say that often methods from like design of experiments work quite well for this purpose, as long as we equip our reduced order model with certain guarantees on a posteriori adaptivity, for example. Okay, so with this core idea, how do we leverage AI? And there's sort of 3 kind of meta steps that we always follow, and we'll apply these steps in different ways over the rest of the talk. So the first is, as I just mentioned, training, where we're going to pay the price of solving this expensive model at a handful of points that I'm going to denote by D-training, and collect simulation data. And this simulation data can take the form of sort of field variables, scalar quantities characterizing quantities of interest, and so on. Number 2 is I'm going to apply machine learning algorithms to that data to identify structure. I'll discuss a few approaches that we leverage to identify underlying manifolds in the solution state space, as well as sort of autoregressive structure in the quantities of interest that are present. And number 3 is reduction, wherein we leverage all the structure that we learn in step 2 in order to reduce the cost of solving the ODE at the remaining points in parameter space that are of interest. Okay, so I'm going to first, so take this as a template meta algorithm that we're interested in. How does this algorithm apply to sort of classical POD-Galerkin methods? So many of you are familiar with model reduction, I'm sure. And there's this method that's been out in the literature for multiple decades now known as POD-Galerkin. And it turns out that that algorithm also fits this sort of 3-step process. And so to ground this talk, I'm going to first present how POD-Galerkin views these 3 steps. So step 1, as I mentioned, is training. So we start with, let's say, 1 point in parameter space. This defines an initial value problem. And they run a transient dynamic simulation where I basically time integrate the ODE of interest at the top with mu frozen at a certain value of the parameters. And at every time instance, I save the state vector. And I concatenate those vectors together to form an n by t matrix, where n is the degrees of freedom of the system. That is the number of elements of our state. And t is the number of time steps I've taken. So after completing 1 simulation, I get an n by t matrix. I then can repeat this training exercise at different points in parameter space, and I populate this concatenated overall matrix that we call the state snapshot matrix. Step 2 is to apply machine learning. And so the POD-Galerkin method applies a very rudimentary method for subspace identification, which is PCA, which I hesitate to even call machine learning because this has been around now, I think, for over 100 years. But the main idea is we take our state snapshot matrix, we compute the thin singular value decomposition and truncate the left singular vectors to obtain a small number of column vectors phi, which we can actually intuit as representing the principal components of the spatial simulation data. Because typically our state vector X represents some kind of field variable, whether it's mass, momentum, and energy in fluid dynamics or the displacement in continuum mechanics, but it represents that field variable at different discretized points in space. So if we compute phi here, the left singular vectors of this matrix, it's essentially the principal components of our spatial simulation data. So then step 3 is to perform reduction. That is, how do we leverage these principal components to achieve our objective, which is to reduce the cost of simulating our dynamical system at many points in parameter space. So what POD-Galerkin does is it approximates the state vector X as a linear combination of the columns of phi. So we approximate X as X tilde, which is enforced to be expressed as phi X hat, where X hat are the generalized coordinates, usually on the order of about 100. That represent the contribution of each of those POD modes to the overall solution. So that's a kinematic approximation that restricts our solution to evolve in a low-dimensional linear subspace. So then what we do is we take our governing ODE. I've suppressed dependence on mu for notational convenience. We can conveniently kind of represent this ODE system as a residual, in terms of its residual, which is the misfit between the left and right-hand sides. I've defined that below. So if we take this residual, what POD-Galerkin does actually is it computes the velocity that minimizes the L2 norm of the ODE residual. And so you're probably familiar with the topmost equation, which is just the Galerkin projection expression. But if you think about it a bit more and you recognize that the matrix phi is orthogonal, you can immediately recognize that this actually is an expression of a minimization property where the velocity we're computing is the minimizer of the ODE residual over all elements of the range of phi. And so this optimization property is quite nice. However, we recognize that in order to integrate the ODE, either the high fidelity ODE in the middle or the Galerkin ODE on the right, we must introduce a time discretization method. Let's imagine it's a linear multi-step scheme, and I've written sort of the general expression for a multi-step scheme at the bottom. We obtained a system of discrete equations, a sequence of those at each time instance n. And I'm going to refer to that as the O delta E because it's sort of the discrete system that arises, the sequence of discrete systems arising from discretizing an ODE. And I've colored the rightmost box here red because we've actually, this color red is meant to imply that we've lost any notion of optimality that we had at the ODE level. And this was sort of an interesting discovery we made over 10 years ago now, which is that if we imbue our ODE model with residual minimizing optimality, and then we apply time discretization, then in general, you cannot prove that the resulting sequence of discrete solutions, x hat n, exhibits any notion of optimality whatsoever. So by applying optimization and discretization in this way, we actually lose optimality in our time discrete solution. So what we developed and proposed was this, what we call LSPG ROM O delta, or least squares Petrov-Galerkin method, which flips the order of time discretization and optimization. And so if we first discretize and then we perform a residual minimizing approximations at the time discrete level, you can kind of obviously see that our actual sequence of discrete solutions exhibits optimality, which is a really nice property. Among other properties, among other nice attributes, we show in our work that this leads to a nice result theoretically, where we are sequentially minimizing the new contribution to the a posteriori error bound at each time instance. And we also observe that this approach really improves predictive accuracy for turbulent flows. And there's a lot of kind of theory that underpins why that is the case that I don't have time to get into today. I'll also point out that others have looked into residual minimizing ROMs, and I have a recent paper with Eric Parrish that generalizes this notion of sort of spatial and temporal projection into a general windowed space-time model reduction framework, where we need not perform optimization over a time step. We can perform optimization over an arbitrary time window that we can align to the sort of spectral properties of our trial basis. So that's sort of the lay of the land in terms of how you perform reduction using these sort of core 3 steps, and PCA. So just to give you sort of insight into how this works, here's an example that is derived from that, that captive carry problem I showed earlier. And I'm going to solve the unsteady Navier-Stokes equations, Reynolds number 6 million, Mach number of 0.6. The spatial discretization I use here is yields about 1 million degrees of freedom, and I'm going to take on the order of 10,000 time steps. And all of our sort of discretizations have been verified and validated. So here is the original computational mesh, and I'm showing at the top here the equation that arises at each time step of our LSPG model, right? We're minimizing the L2 norm of the time discrete O delta E residual over the range of phi. And so what you'll recognize if you're, a numerical analyst is, even though I'm computing a low dimensional vector, because I'm doing that by minimizing the sum of squares of a huge number of residual elements, this approach, just as written here, will not yield computational cost reduction. And that's because the cost of this is still scaling linearly with the original dimension of the problem. That's also the case with our high fidelity model. So sort of in terms of a complexity analysis, we haven't actually made any headway here. The way that we achieve computational cost reduction in practice is by replacing this L2 norm with a semi-norm that is derived by data. And critically, the semi-norm requires only computing the residual at a small number of elements of our computational mesh. In this example, I'm showing that part of the mesh shown in red here. And in this example, we're using less than 1% of the overall mesh in order to evaluate or approximate my residual norm. And this is really exciting because it allows us to do HPC caliber simulations on my laptop. If I don't have to load in the entire problem, I only have to load in a handful of cells, and I can, I'm computing a low dimensional vector, then this can all fit in very compact memory and can incur a small computational footprint. So let's see how this approach works on this captive carry problem. I will note that the Galerkin approach of project then time discretize was unstable in this case, whereas our LSPG model is stable and very accurate. So in this case, our LSPG model is consuming half an hour on my laptop, and the original model was 5 hours on 48 cores. So we're achieving 2 orders of magnitude computational cost reduction, which is right in sort of the wheelhouse of what NASA was looking for in their challenge that they articulated earlier. And we're incurring sub 1% errors in time average drag. So this is very exciting, and I should just emphasize here that the parameter that we're varying here is effectively time, in that we are training the ROM over a finite time window and then allowing it to run further in time. And that's how we're able to, bootstrap data collection over additional analyses. So a natural question arises: if these results are so great, then why doesn't everybody use ROMs for their day-to-day analysis? And there's a lot of really good reasons for this. And I'm going to sort of go through sort of the outstanding challenges in model reduction as of, let's say, 3 years ago, and how we've done work to try to get at some of these sort of core challenges that preclude these models from being used in typical sort of day-to-day analysis settings. So outstanding challenges. Number one is that the first assumption that I made, that kinematic approximation on, I think, slide 5, is actually extraordinarily strong. In many cases, even a simple sort of 1D shock propagation problem, you can convince yourself that there exists no low-dimensional linear subspace that can accurately capture the solution over the entire trajectory of solutions. And that's known as the Kolmogorov-width limitation of linear subspaces. Basically, this original assumption invalidates model reduction for a wide class of problems that are dominated by advection, or makes it very hard to get these methods to work in those cases. And so we did some work last year that gets at this problem in a core way by introducing nonlinear manifolds and learning those manifolds via deep learning techniques. I'll talk about that first. Second is that important physical properties are generally not enforced by model reduction. So whether we take Galerkin or LSPG, these are both essentially residual minimizing projection schemes. And so while this is sort of good in the sense that we're minimizing the misfit of our approximation with respect to the high fidelity truth model, it doesn't guarantee anything about the reduced order models inheriting properties that are important to the dynamics, right? Like, let's say, symplectic time evolution, for example. And so to get at this, we've developed a couple different approaches. We've actually directly addressed the Hamiltonian and Lagrangian dynamical system case in other work. But today I'll talk about how we enforce conservation exactly as is relevant to finite volume discretization of conservation laws. And number 3 is that error analysis is difficult. So our field is, there are a lot of great researchers working in model reduction, but many of them have a mathematical analysis background. And so the pervasive mentality of characterizing errors in model reduction has been to derive rigorous either a posteriori or a priori error bounds. And while rigorous error bounds are useful in many cases, it's not the only way to characterize error. And in many cases, especially for long timescale integration problems, rigorous error bounds can be extremely pessimistic. And so we sort of developed a new family of techniques for error analysis that's rooted in statistical learning theory, where we aim to generate statistical models for the error incurred by a reduced order model, such that we can deploy these models very quickly and then rapidly characterize the errors incurred by those models, sort of in a statistical sense, and also to facilitate integration with UQ applications. So first, I will talk about this first topic, which is overcoming the linear subspace assumption, the limitation incurred by making this linear subspace assumption. Okay, so first, to motivate this, I'm going to first get into a mathematical definition of the Kolmogorov-width limitation of linear subspaces. So I'm not sure who on this call is familiar with the Kolmogorov-width of a problem, but I'm going to assume no prior knowledge, and I'll just get into sort of a basic definition of the Kolmogorov-width of a problem that will hopefully elucidate why we need to do this work. So the first term I'll introduce is calligraphic M, which is the set of all solutions that I obtain over time and parameters for my initial value problem. Right. So this is nothing more than the set of solutions over all time and all parameters. Number 2 is calligraphic SP, which is the set of all p-dimensional linear subspaces of my original state space. This is also known as the Grassmann manifold. Essentially, you can think of this as any set of linear subspaces that I could define to approximate the solution manifold. The next thing that I will introduce is DPM, which is the Kolmogorov p-width of the problem. And what this is, it's the infimizer over all elements of this Grassmannian of p infinity ms, where p infinity ms is the L infinity projection error of the manifold onto that particular subspace S. And so if you stitch this all together, you get sort of an inf sup inf condition, which essentially intuitively what this means is if my Kolmogorov p-width is below a level epsilon, this means that there exists some linear subspace of dimension p that can represent all elements of my solution manifold with accuracy greater or with error less than epsilon. Okay, so while this L infinity projection error is useful from a sort of an analysis viewpoint, but it's very challenging to compute with. So I'm going to just replace this L infinity projection error with the L2 projection error. And so we can get a modified notion of Kolmogorov-width if we replace the L infinity projection error with the L2 projection error. And so with this modified definition of Kolmogorov-width, I will now plot this for a candidate problem as I increase the dimensionality P underpinning the linear subspace. So if I plot the error versus the dimension P, we get this nice exponential decay, which you often see in sort of PDE problems. So to get a handle on this, let's now project just the L2 projection error of the solution manifold onto a POD subspace that I compute by some data collection mechanism. And if I do that, I obtain this blue curve shown here. And we can interpret the gap between the blue and black curves as representing the training deficiency. That is the lack of data that went into my definition of my POD basis. Because if I had completely sampled the solution manifold, these two curves would coincide. So what I'll now plot is the L2 error of an LSPG reduced order model built from the subspace that generated the blue curve. And if I do that, I get the green curve shown here. And the gap between those curves is known as the closure error. It's essentially the failure of my reduced order model to generate the L2 projection error of the true manifold onto that subspace. And there is work that goes into directly trying to characterize and reduce this closure error, which often involves including sort of non-Markovian terms in the equations governing the reduced order model. Okay, so we've introduced these three curves, but I'd like to kind of return to this black curve and ask the question of whether or not this is actually a good result, right? Is exponential decay sounds good, but is it actually sort of a good result from an approximation viewpoint? And I would argue if we think about just general manifold approximations, this is actually a really bad result. Because what I didn't tell you in this plot is that I generated these results for a problem with only two parameters, mu1 and mu2, and time. And so because it's a well-posed initial value problem, I know that the solution manifold itself is of dimension 3. And so if I kind of draw a vertical at the dimension 3, and I look at the error in the theoretically optimal linear subspace for a reduced order model of that dimension, then what we, for a subspace of that dimension, we see substantial error. This is on the order of 5% error when my linear subspace dimension matches that of the true underlying manifold. And this is a major problem because what it says is that no matter how much data I throw at the problem, if I live with a linear subspace, I will always have substantial error, even when I've matched the dimension of the original solution manifold. And that phenomenon comes from the fact that I'm limiting myself only to linear subspaces. And so the goal of this work really is to overcome this fundamental limitation we cannot overcome with linear subspaces by looking into nonlinear manifolds and then ways of practically computing those manifolds. So we aren't the first people to look at this Kolmogorov-width limitation of linear subspaces. It's actually a fairly active field in model reduction. But most of the work that's going on right now, or went on at the time that we executed this research, fell into loosely 3 buckets. The first was to transform or update a linear subspace. And so many of these methods like freezing coordinate transformation, shifted POD, snapshot transformation, Lagrangian formulation, and lax pairs. What these all do is essentially take a linear subspace and sort of advect the modes, or move the modes, or translate them, or somehow modify those modes as time or parameters evolve. And while that can often work much better than using a fixed basis, usually this requires some very problem-specific knowledge of the characteristics underpinning the dynamical system. So we may need to know, for example, how the solution advects in order to advect the modes properly. And also, I would point out that these methods don't consider manifolds of general nonlinear structure. They're fundamentally tied to this notion of a linear approximation and try to overcome that in a bit of an indirect way by moving that linear approximation around as the solution evolves. And so I would argue that this is not really getting at the core of what we want to overcome in terms of the Kolmogorov-width limitation of linear subspaces. Secondly, people have also looked into a priori construction of local linear subspaces for different regions of the space or time domain or the state space. And while this can also, again, work better than a fixed linear subspace, we, again, are not really considering manifolds of general nonlinear structure. So at the time that we did this work, there were really, as far as we knew, 3 papers that attempted to get at true model reduction on nonlinear manifolds. Unfortunately, these methods were either kinematically inconsistent, meaning that the velocity computed by these methods did not live in the tangent space of the manifold. So that's an inconsistency right from the bat. Number 2, these are, in one case, it was actually limited to piecewise linear manifolds. So even though the exposition tried to get at some nonlinear manifold ideas, really this fell into the first 2 buckets here of essentially using piecewise linear manifolds. And in all 3 cases, the solutions lack any notion of optimality with respect to the true solution, which, as we've seen in our work, can lead to fairly poor performance over long time intervals. So the goals of the work here were to overcome shortcomings of existing methods, that is, imbue model reduction or imbue manifolds with general nonlinear structure, ensure kinematic consistency, and also satisfy some notion of optimality in the approximation that we're generating from the reduced order model. And secondarily, this manifold should be practical to construct. Ideally, we would require no special problem knowledge, and we would use the exact same training data as POD. Hopefully, we wouldn't need any other information to construct our manifold, just to make it practical at scale. And so to get at the first of these, we developed a new set of projection schemes known as Manifold Galerkin and Manifold LSPG that are generalizations of subspace Galerkin and subspace LSPG that I presented earlier. And secondarily, for problems laid out on sort of on a computational grid, like finite element, finite volume methods, we developed a deep convolutional autoencoder approach to building this manifold in a practical way. So first, I will just talk about Manifold Galerkin and LSPG. This has nothing to do with really AI or deep learning or anything like that. It's just differential geometry and dynamical systems. The second part, we'll get into some of these AI-driven approaches to compute the manifold. Okay, so in terms of subspace Galerkin and subspace LSPG, if you recall earlier, our kinematic approximation essentially said that I'm going to restrict my solution to live in the range of phi, which is the set of all solutions that can be expressed as phi x hat, with x hat a low-dimensional vector. So if n equals 3 and p equals 2, we get essentially a plane in R3 that associates with this linear trial subspace. If I then develop my kinematic approximation from there, my state lives in that linear subspace as written here. And then if I apply the chain rule, because my POD basis is not time dependent, we obtain the same expression essentially for the velocity, that it must live in the range of phi. So now if we take a sort of a parallel view for nonlinear manifolds, viewed from the extrinsic perspective, we can write any nonlinear manifold as, in terms of its parameterization function g, that must be, in our case, must be continuously differentiable. And we express this nonlinear manifold as the set of all solutions g x hat with x hat in RP. And so for a certain g, we might get this sort of curved structure in R3. Note that we've merely replaced phi with a nonlinear function g that maps from a low to a high dimensional space. So if I draw out the kinematic approximation and I restrict my state to live in this manifold, you can write this algebraically simply as x tilde is equal to g of x hat, which ensures that we can have sort of general nonlinear structure. We don't need to have, piecewise linearity if we leverage this approach. And if we apply the chain rule, we sort of obviously see that the velocity must live in the tangent space of the manifold. And so by doing this, we enforce kinematic consistency. Okay, so let's think about how we would then apply a dynamics approximation, which is essentially reduction. So for linear subspace, given this basis phi and the kinematic approximation on the last slide, we say that my Galerkin model is derived by, again, sort of minimizing the ODE residual at each point in time, which associates with this dynamical system model, right? dx hat dt is equal to phi transpose f. And the LSPG counterpart associated with a residual minimizing approximation at the time discrete level, right? Over the kinematic approximation that was developed for the state. So in parallel, how would we develop these if we are given g instead of phi? So if we're given the function g, then we can compute the velocity in the Galerkin setting as minimizing over all elements of the tangent space of the manifold, the ODE residual, which if you stare at this a bit, you can convince yourself it associates with the ODE shown there. And the nice thing about this is that we don't need any, because the ODE is expressed in terms of the parameterization coordinates. I'm guaranteed to, no matter what integrator I use to integrate this ODE system, I'm guaranteed to always remain on the manifold. And so we don't need to develop any fancy time integrators or anything like that. We can simply apply any valid time integration scheme for ODEs to these manifold parameters, and we're guaranteed to reside on the manifold, and have also time continuous optimality. If we apply the same sort of approach to the time discrete level, we obtain this result, which is again a residual minimizing statement at the time discrete level. And so by developing these approaches, we can now sort of say that we've come up with two counterpart reduced order models that satisfy residual minimization at the time continuous and time discrete levels. One interesting theoretical result that emerges from this is that we can actually come up with limiting equivalence conditions for these two models. So it turns out that manifold Galerkin and LSPG are equivalent under certain conditions. Number one is that we have twice continuous differentiability of the manifold itself. We ensure that the difference in generalized coordinates between time steps is on the order of the time step itself, so we can't have discontinuous jumps in the solution. And we also assume that we take the limit as the time step goes to 0. So this makes sense. The third condition is the key intuition for why this makes sense, because as the time step goes to 0 under conditions of sort of sufficient smoothness, we can guarantee that time discrete optimality is equivalent to time continuous optimality. So really, you can view LSPG here as a generalization of Galerkin in the limit of the time step going to 0. We also developed error bounds for manifold and LSPG and manifold Galerkin. And really, it's a fairly simple statement that under Lipschitz continuity and a sufficiently small time step, you can bound the error in both the Galerkin and LSPG solutions by very similar terms. The gray term on the right is just the recursive term in the bound and is the same in both cases. But what differentiates them is the new term at each time instance, which is nothing more than the L2 norm of the discrete residual. And because that's exactly the term minimized by manifold LSPG, we know that manifold LSPG is sequentially minimizing the error bound, which gives us some nice sort of a priori guarantee that we'll have a fairly good approximation. And I'll show later on in the numerical results how we observe that LSPG, even on simple problems, tends to generate better results than Galerkin projection. Okay, so this sort of like is a high-level overview of how we developed manifold Galerkin and manifold LSPG projection schemes, given some parameterization function G. But I did not prescribe how I constructed this manifold from training data. So now I will get into that. And that's sort of the second part of this aspect of the talk. Okay, so the question is, how do we build this parameterization function from data? And the main requirement that we need from any kind of machine learning method that would learn this is that it must provide the mapping from the low dimensional to the high dimensional space. We don't need the mapping from the high to the low dimensional space. And so it turns out a lot of methods for manifold learning in machine learning in AI actually don't provide the requisite low to high dimensional mapping. So for example, isomap, local linear embedding, Hessian eigenmaps, and t-SNE, they provide the high to low dimensional mapping. And so those methods aren't really valid. So in principle, we could use any method that learns the low to high dimensional mapping. Some examples are self-organizing maps, generative topographic maps, kernel PCA, and so on. But what we're going to use in this work is deep convolutional autoencoders. And that's for a few reasons, but I'm sure many people here are aware of what an autoencoder is. But if you're not, basically it's an neural network architecture that tries to map inputs to outputs through a bottleneck layer in the middle. The first part of the architecture is called the encoder, going from high to low, and the second part is called the decoder, going from low to high. And the networks on either side are parameterized by some parameters theta. And so the idea is if we're able to train an autoencoder that can successfully copy the state vector to a nearby copy of itself for some value of the parameters, then we know that the decoder itself provides an accurate parameterization of the manifold, because essentially the codomain of that function covers all of our training samples, and there's some latent representation x hat that can be input to that function in order to generate those results. And so the intuition we're going to use is to basically build take an autoencoder architecture, train it, and then extract the decoder to define the manifold. We're going to use convolutional autoencoders because we're going to, at least at first, consider kind of simple problems from fluid dynamics that are defined on a regular Cartesian grid, or basically a regular grid that is very similar to how you might lay out, to how image data are laid out. And also we want a lot of the inductive biases that are baked into convolutional architectures, like translational invariance properties and so on, because we often have sort of moving shocks and discontinuities that we would like to be able to capture no matter where those shocks or discontinuities appear in your physical domain. Okay, so how does this work? So if you recalled earlier in the talk, we took our snapshot matrix and computed the SVD to extract the principal components, or POD modes. So instead here, we're going to take the exact same training data, and then rather than computing the SVD, we're going to introduce an autoencoder architecture and try to copy every column of X to a version X tilde. And we're going to try to minimize the Frobenius norm of the error between those two matrices. And we're going to compute the parameters of the autoencoder in order to minimize that functional. And then, as I mentioned, we're going to define, after we finish that, we're going to apply some kind of SGD method. We are going to define the nonlinear trial manifold by setting that G parameterization function equal to the decoder. And I just want to call out here that, in contrast to some of the other work that's been done in this sort of domain, we're using the same snapshot data as POD, and we don't require any specialized problem knowledge. Okay, so now if we return to how we did the dynamics approximation, what we see here is that if G is defined by an autoencoder, then really our reduced order models are directly integrating deep learning predictions through everything involving G with the computational physics code itself. And so doing this requires, effectively what we're doing is we're basically putting in a kind of generative or decoder model. We're feeding that into our physics evaluator, if you want, and then we are trying to minimize the error as the physics code defines it, and backpropagating that error to the latent variables. And so this requires essentially hooking up PyTorch with our PDE simulator in a very intimate way. where every iteration of our nonlinear solver here is going to call, the autograd capability in PyTorch. Okay, so here are the numerical results. Just right now we have this going on very simple examples. My colleagues at Sandia are working on applying this to much more complex problems. We actually do have an AIAA paper that applies this to hypersonic three-dimensional external flows, which is I think, kind of worth checking out. But for this paper, we just applied it to very simple problems to try to understand exactly how this approach can overcome some of the deficiencies of linear methods. So 1D burgers, 2D reacting flow. In each case, we're going to use 2 parameters to characterize the problem. And here's just a glimpse of our autoencoder architecture that we use for the 2D reacting flow case. You can check out more details in our paper. And again, just to reemphasize, we're only using the decoder, which involves deconvolutional layers to define the manifold. Okay, so here's to give you some intuition into how this actually works. So I'm not going to consider a ROM right now. I'm just going to consider the kinematic approximation and the kinematic error itself. So on the left here, I'm showing the full order model solution. And in the middle, I'm showing the POD reconstruction error. And so on the top, I'm in the middle column here, I'm showing the generalized coordinates that are traced out. If I project optimally each snapshot of the full order model onto the subspace spanned by the POD modes, I'm using 3 modes in this case. And on the bottom, I'm visualizing the reconstructed solution. And so if you're a fluid dynamicist or you've worked in model reduction, this is not at all surprising, because if you have 3 sort of spatially fixed modes and a moving discontinuity, you really can't do much better than what's shown here to reconstruct the solution. And that's because of this fundamental limitation of linear subspaces, right? Because the shock is moving, it's an advection dominated problem that is not well represented by fixed spatial modes. And so this is a problem that, mapping it back to the Kolmogorov-width discussion, is poorly, sort of exhibits poor Kolmogorov-width decay. So now what I'm going to show you is the same problem, the same reconstruction error, the same training data, but now using an autoencoder instead of a POD representation. And again, I'm using only 3 latent variables. And what we see here is that the reconstruction is almost perfect, right? We get nearly perfect reconstruction of the full order model, again, but with only 3 dimensions. And the difference only between the middle and rightmost columns is that I'm using a nonlinear autoencoder instead of a linear POD basis. And so this intuitively is a really great result. If you've worked in model reduction before, you may not believe these results. I initially didn't believe these results when I first saw them for my postdoc, but really it kind of goes to show how impressive these autoencoders can be in terms of representative power that we can imbue our reduced order models with. Okay, so now let's introduce this into an actual reduced order model framework with projection. And so I'm going to show, here's the full order model on top and the POD LSPG ROM in the middle of dimension 5 this time. And as expected, because we have an advection dominated problem, the POD method is quite poor in both cases. If I use the same training data and same latent space dimension, we obtain the results shown here. And we see in contrast, extremely good results. And I'm not using any different data or even a higher dimension in the latent variables. I'm only changing the fact that my decoder is now nonlinear instead of linear. And so these are, really exciting results. So if I go back to the plots that I showed earlier, so that cartoon that I drew out was really the reacting flow case in the middle here. I'm going to populate the results on the left for Berger's equation. And these are the familiar sort of plots that I showed, a few slides ago, where I'm plotting the dimension of the manifold, the subspace LSPG error, the L2 projection error of the manifold onto the basis, as well as the Kolmogorov-width decay. So if I now what I'm going to do is plot the L2 projection error of the true solution manifold onto the manifold defined by my convolutional autoencoder. And if I do that, I obtain these black points shown here. And right away, you see a huge improvement over even the theoretically optimal linear subspace. And this is a really important result because it shows that, really to overcome this fundamental deficiency, all we had to do was introduce a nonlinear decoder, and we can immediately get multiple orders of magnitude improvement in the kinematic approximation itself. If I then solve a reduced order model, my manifold LSPG, using this autoencoder, I obtain the pink points shown here. And these are only slightly worse than the L2 projection error on the manifold itself. But we see it's orders of magnitude better than subspace LSPG. Again, not using any different data or dimension or even projection approach, just using a different decoder. And so hopefully this convinces you that this method is able to overcome and break this Kolmogorov-width barrier. Yeah, and I'm also plotting here now the manifold Galerkin results shown in blue. And what we see is, at least on the left in the Burger's case, we see that a manifold LSPG does yield better results than manifold Galerkin. And we hypothesize that this arises from the fact that manifold LSPG sequentially minimizes the error bound as opposed to manifold Galerkin. So this is further evidence that we've obtained now in the manifold case that LSPG projection can outperform Galerkin in many cases. I'll quickly now go into a sort of physical property preservation. So if you're familiar with finite volume schemes, which underpin, basically the vast majority of approaches in fluid mechanics for discretizing conservation laws, you'll know that this ODE arises from basically applying a finite volume scheme to the underlying conservation law. And so if we think about a conservation law and like how we would discretize that with a finite volume scheme, we basically decompose a domain into a set of control volumes, and then we enforce conservation over each control volume. So in this case, each element of the state vector is the average value of a conserved variable. Usually in three-dimensional Navier-Stokes, we have density times each of the three velocity directions, as well as density times the energy. So we have 5 conserved variables, and each element of the state vector is the average value of one of those conserved variables over one of the control volumes. The velocity represents the combination of flux and source of that conserved variable within the control volume, such that the ODE residual is just the rate of violation of conservation of a variable in a control volume. So that's how we interpret the ODE residual for finite volume schemes. If we introduce a time discretization method, let's say it's an atom scheme, then we associate conservation violation. Then we associate the time discrete residual R with the amount of conservation violation of a variable in a control volume over a time step size. And so because the high fidelity model of the full order model is setting each of these residuals to 0, we can immediately deduce that conservation is the intrinsic structure enforced by finite volume schemes. So with this interpretation in mind, let's return to our manifold Galerkin and LSPG models, right? These are both basically minimizing the time continuous and discrete residuals over the manifold itself. And so in the context of finite volume schemes, this means that we are basically minimizing either the rate or the amount of conservation over a time step. And so while this is nice, right, we're minimizing the amount we're violating conservation, neither is actually directly enforcing conservation. And so what this means is we can get, spurious generation or dissipation of mass, momentum, and energy in our solution that can yield sort of poor performance over long time intervals. And so to overcome this, we basically propose a very simple modification, which is to take these objective functions and introduce nonlinear equality constraints that enforce conservation not over every cell, because that would be equivalent to the full order model, but over subdomains of the problem. And we can do that as long as the number of subdomains is sort of less than the number of overall cells in the problem. And so on the left, for conservative manifold Galerkin, you see that basically what we're enforcing is conservation over subdomains of the problem. Rather, we're enforcing that the rate of conservation violation is 0 over subdomains. And on the right, we're enforcing that the amount of conservation violation over a time step is 0 over subdomains as well. And so one specific interesting example of a subdomain is just the entire domain, right? So if I introduce, let's say, constraints that enforce global conservation, then I'm guaranteed, as long as there's a feasible solution, that my reduced order model will be exactly conservative over the entire domain. And that's a really nice property because note that we're generating trajectories that aren't approximately conservative. They are actually exactly conservative over certain subdomains, which is a really nice property to imbue your reduced order model with. We have a nice sort of theoretical result in the paper. We have a whole lot also additional results in the paper related to sort of hyper reduction of these approaches, how you can sort of define the number of subdomains and so on. One result that I'll point out here is that in one of our error analysis results, we basically show that the error in the conserved quantities sort of globally or over the subdomains can be bounded as shown here, which basically means that the error in the conserved quantity depends only on the decomposed mesh itself. And so if we do global conservation and we have no source terms, then the error in my globally conserved variables is due entirely to the error in the flux along the boundary. So basically what this means is that we're much more sort of forgiving to errors introduced in my reduced order model, because I don't need to sort of respect the conservation laws locally within the domain in order to obtain pretty good global results in terms of the globally conserved variables. So just to give you a quick taste of this, here's what I showed earlier with LSPG ROMs for both the POD subspace and the autoencoder. It turns out that the solution error in those cases is 13% and 0.5% respectively, which is quite good in the autoencoder case. The conservation violation was still around 1%. So what we can do is imbue both of these models with conservation constraints globally, and we obtain sort of visually similar results, but we obtain essentially machine zero error in global conservation violation. So that's a nice property that if we were to run this out over longer time intervals would likely lead much better results. Okay, so to provide a quick outlook, here are the conservative manifold Galerkin and LSPG models. I want to re-emphasize the interpretation that these models are integrating computational physics and deep learning directly. And these are effectively projection-based latent dynamics models that enforce conservation. And if you think about this in sort of the greater context of AI, there's a whole host of research that tries to develop latent dynamics models, but these are purely data-driven, meaning that they learn some kind of compression followed by time time series model like an LSTM that can predict the evolution of these codes over time and parameter variation. But because most of those methods are sort of purely data-driven, they never requery the high-fidelity physics code that can help us navigate and understand the error in those models. And so because our models in these reduced order modeling approaches are directly minimizing the error incurred, the error as defined by the high-fidelity physics code, we often get much better results, and we have stronger guarantees on error as well as the ability to quantify error. Gradient computation, we use AutoGrad to compute the decoder Jacobian. And then I'll mention ongoing work. So we're pursuing hyperreduction, and we've also recently published a paper where we generalize this sort of optimization structure to general sort of attributes that we'd like to imbue our reduced order model with. And so we associate those with sort of equality and inequality, kinematic and dynamic constraints. So if you're interested in a more general approach to optimization-based model reduction that can enforce a range of interesting physical properties, you can check out our paper below, which has recently been accepted for publication in IJNME. And then I'll very briefly get into this last topic of error analysis. Okay, so if you recall earlier, I presented this a posteriori error bound for manifold Galerkin and manifold LSPG. And so one natural question you might ask is, hey, why can't we just use these error bounds for error estimation, right? We can, in principle, estimate all the terms in the right-hand side here, and then run our reduced order model, take then an error bound, and then use that to characterize the error. Unfortunately, if you would draw out the recursion in the bound, you get the terms shown here. And so what we get are stability constants that grow exponentially in time. And as a result, that means that these error bounds are often extremely pessimistic, and it's not uncommon for any error bound for nonlinear dynamical system ROMs to have basically overestimate the error by 3 orders of magnitude. So in many cases, especially for practical problems, these error bounds are not really pragmatically useful. I would also add that many of our applications really care about sort of quantifying uncertainty, right? So uncertainty quantification applications would like ideally to make use of the ROM as just introducing another source of uncertainty into our ultimate analysis. And we can't get at that either with these deterministic bounds. So the main idea of what we're going to pursue here is to develop a statistical model for the reduced order model error that is more accurate, basically that has sort of, ideally be unbiased estimate of the error with low variance, but also that could have sort of validated statistics that we can integrate into our uncertainty quantification applications. So the way that we're going to do that is by leveraging a key observation, which is that reduced order models often generate quantities that are very cheap to compute, yet remain highly informative of the error. And effectively, these are the residual-based quantities that we are obtaining because our deep learning predictions are directly querying the high-fidelity physics model itself, right? So at every time step, wherever we're sampling the residual in that sample mesh that I showed, we are getting a sample of the residual of the high-fidelity model, right? This is essentially a measurement that says, how far away is my reduced order model from exactly satisfying the governing equations at that local point in space and time. And so what we can do is adopt a machine learning or statistical learning viewpoint of this and interpret all those residual-based quantities that we're producing with the reduced order model as representing good features for predicting the error. And so the plot that I'm showing here is a very simple example where the x-axis is a simple to compute residual-based feature, and the y-axis is the error in the reduced order model that's typically very hard to compute. And so in this simple case, we get a very simple linear correlation, but in more complex problems, it's a more sophisticated relationship. But nonetheless, the idea is we're going to apply machine learning regression to generate a mapping from residual-based quantities that the ROM produces for free to a random variable for the error. And we call this machine learning error models, or MLEM. We have a few papers on this. So to formulate this, like sort of what inductive bias should we put into our model? And so to get at this, let's kind of dive into the characteristics of ROM errors. So here's the error bound I showed earlier. A few of the properties of ROM errors that we see are: number one, ROM error depends on non-local quantities in time. So our reduced order model, our machine learning error model should be able to capture long time dependencies. And we also see a dependence on the residual, right? And so this again reemphasizes that the residual is an important feature for predicting the error. And so the regression model we're going to propose has a combination of a deterministic and stochastic component, where the deterministic component is essentially a regression function that is essentially autoregressive in nature and leverages latent variables. And so these latent variables, or latent dynamics, are important to be able to capture non-local dependencies, which is the sort of green thing that I mentioned above. And the features should be residual based and cheaply computable. And it turns out this simple regression function that I've written out here is a general expression that encompasses a whole host of time series modeling methods, all the way from classical autoregressive models to more modern gated recurrent units and LSTMs. So just as a quick example, here's like what the architecture looks like for an LSTM that fits into that general exposition for a time series model. So how do we bake this into our training process? So what we're going to do is we're going to take the points that we've queried the high fidelity model, and we're going to run our reduced order model as well. And in this case, we're going to collect feature response pairs. So the response we're trying to predict is the error in the quantity of interest Q as computed by the reduced order model relative to the high fidelity model. And the feature vector is a concatenated set of residual based features that we're computing. We then can, take all this training data together and then apply the traditional machine learning approach, right? We randomly divide a training and test, construct a regression function via cross-validation, and then we construct a noise model from the sample variance on the test data. And so I'm running out of time here, but just in a nutshell, basically what our workflow looks like is for inputs, we run the ROM, we get output predictions. The ROM also produces these features, which we feed into a regression model, which then yields a statistical model for the error in the ROM. And then we simply add the ROM quantity of interest prediction to this error model to get a stochastic, statistically validated model for the high fidelity model quantity of interest. So in our papers, we have a whole host of results here. I'm plotting here, this is all using sort of the same overarching framework, but each column corresponds to a different set of features, and each row corresponds to a different regression technique from machine learning. What we see here is that it turns out that RNNs and LSTMs can get extremely accurate results, FVUs, below 0.01. So we're explaining, over 99% of the variance in the data using only, I think in this case, 7 samples of the residual at each point in time. So yeah, that is a very nice result that allows us to basically extend, perform very accurate quantification of the error using modern deep learning methods. So with that, I actually don't have time for questions, but I'd be happy to respond to any questions via email if that's viable. So thank you very much for your time.
All right, thanks a lot. Yeah, so yeah, as Kevin said, he has a meeting in 1 minute, so there is no room for questions, but feel free to contact him. Yeah, thank you very much. Yeah, thank you, Kevin. Yeah,
thank you so much. I really enjoyed it.
Yeah, thanks a lot. Thank you. Take care. Bye-bye.
Bye.